The engineering challenges of a generation ship are staggering. Life supports must be closed-loop, recycling all waste into resources. Plants would provide oxygen and food, but they need light. Artificial lighting demands energy. The ship would need to power its farms and habitats for centuries. Shielding against cosmic rays and interstellar dust would be critical. At even a few % of the speed of light, a grain of sand carries lethal kinetic energy. The hull might need to be meters thick, or include electromagnetic fields to deflect charged particles. Social systems would be equally crucial. A multi-generational crew would need governance structures, education, conflict resolution, and cultural continuity. People would be born, live, and die without ever seeing Earth or the destination. Science fiction imagines all manner of problems: mutinies, genetic drift, loss of mission purpose. Research groups exploring generation ship concepts emphasize that community planning, psychology, and ethics are as important as propulsion. Suspended animation, if feasible, could bypass some social issues by reducing the active crew size. But freezing and thawing humans without damage is not currently possible. Medically induced hypothermia slows metabolism but cannot stop it. Ice crystals form in tissues and cause cell rupture. Future technologies might use cryoprotectants or nanotechnology to prevent ice formation. Alternatively, metabolic pathways could be chemically suppressed to mimic natural hibernators like bears or ground squirrels. Even then, long-term hibernation raises concerns about muscle atrophy, bone loss, and cognitive effects. There is also the question of consent. Would a person willingly sacrifice consciousness for centuries, knowing they would awaken in a future society of strangers? And would the voyage still be meaningful if experienced as an instant? Robotics and artificial intelligence offer different solutions. A robotic probe needs no life support, can withstand acceleration and deceleration phases beyond human tolerance, and can operate for centuries. With self-repair capabilities and redundancy, it might function long enough to deliver instruments to a distant world. Self-replicating probes take this further by copying themselves using local resources. A probe that arrives at a resource-rich system could mine asteroids, construct new probes, and send them further. In theory, such probes could spread exponentially, visiting every star system within tens of millions of years, well within the age of the galaxy. This prospect has been invoked in discussions of the Fermi paradox. If self-replicators are feasible, where are they? One answer is that building such a system might be extremely difficult or dangerous. A malfunctioning self-replicator could become a cosmic grey goo, consuming resources indiscriminately. Ethical considerations may restrain advanced civilizations from deploying them. Artificial consciousness offers yet another path. If minds could be uploaded into hardware that is robust to radiation and low temperatures, then the travelers would not be flesh and blood. They could endure long delays and isolation with ease by slowing their subjective clock. They could replicate themselves with bit-perfect fidelity. They could create copies to accompany different missions. But such beings would face questions of identity, continuity, and connection. If a copy of you travels to a distant star and you remain on Earth, which is the real you? When the copy sends back a message, are you conversing with yourself or another? The cosmic prison may take on new meaning for such entities. The isolation is no longer about physical survival, but about the divergence of minds that once shared a common origin. Across all these scenarios runs a common thread: autonomy. Whether the travelers are humans, robots, or AIs, they must operate without immediate support from home. Communication delays mean they must solve problems, repair themselves, and adapt to unforeseen circumstances on their own. They must become their own civilization. That requirement shapes not just the design of the mission, but the values of the society that launches it. A culture willing to send out such explorers must be comfortable with letting go, with nurturing children it will never meet, and futures it will never see. In that sense, the cosmic prison asks us to redefine connection. We cannot be present everywhere, but we can send parts of ourselves, biological or digital, to experience the universe and report back on timescales our descendants can appreciate. The first truth is a disarmingly mundane one. In daily life, nothing ever makes you confront the finite speed of light. Even a transcontinental flight feels immediate in the scope of a human life. Turn on a light and the room is illuminated instantly. For most of human history, our senses and our brains were tuned to meters and minutes. We carried fire, watched the sun cross the sky, gauged the seasons by the length of shadows. On those scales, light moves so swiftly that it feels infinite. When you walk across a room, light crosses it nearly 7 million times before you do. The laws of physics have placed us in a world where causal signals appear instantaneous for the lengths of bone and muscle we inhabit. That everyday experience is the first bar of the prison we live in, because it hides the wall in plain sight. A speed limit that never intrudes on the morning commute is easy to forget, until you start to measure the world by star-to-star distances. On those ancient days when our ancestors sat around campfires, the distances that mattered were how far a spear could fly or how long a day's walk would take. They measured their world in paces, the span of an outstretched arm, or the number of heartbeats between breaths. The foot, the cubit, the yard are all anthropocentric. Light crosses a yard in a nanosecond. The signals in your nervous system move slower than that. All of our early technologies, stone tools, bronze, iron, functioned in a regime where the finite speed of light was irrelevant. Even as we built ships to cross oceans and telescopes to gaze at the heavens, our intuitive sense of time and distance remained anchored to the human scale. The moon's monthly cycle, the years turning, the horizon line, these were our coordinates. In such a world, the cosmic speed limit is an abstraction with no bearing on daily survival. It is part of the reason we have never had to develop a gut feeling for the difference between a light second, a light hour, and a light year. As scientific instruments improved and our curiosity grew, we started to measure the speed of light itself. Ole Homer's 17th century observations of Jupiter's moons hinted at a finite value. James Bradley refined the estimate by watching starlight shift due to Earth's motion. In the 19th century, Michael Faraday and James Clerk Maxwell united electricity and magnetism and showed that electromagnetic waves must travel at a fixed speed. That calculated speed matched the measured speed of light. They realized light was an electromagnetic wave. Maxwell's equations predict a universal constant c. The constant appears again in Einstein's equations and in modern quantum field theory. It is not simply a property of light, it is a property of the vacuum. Even gravitational waves, ripples in space-time itself, travel at c. When the LIGO detectors first observed those waves from colliding black holes, they arrived on Earth 1.3 billion years after the event, and exactly on time. Those waves were telling us that space-time's own vibrations respect the same limit that photons do. The constancy of c permeates our understanding of physics. It is the baseline rate at which information flows and reality evolves. From the perspective of a creature who never leaves its home planet, the Earth itself seems vast, and a lifetime is long. Yet even the farthest reach of our species, the farthest any human artifact has travelled, is a mote compared to the distances between stars. Voyager 1, launched in 1977, is the most distant human-made object. After 4.5 decades racing out of the solar system, it has barely crossed one light day, meaning that if it sent a radio message today, it would take 24 hours to arrive. Voyager travels at about 17 kilometers per second. At that speed, NASA calculates it would take more than 73,000 years to reach Proxima Centauri. That star, our nearest stellar neighbor, lies roughly 4.25 light-years away, more than 40 trillion kilometers. At the cosmic speed limit, the speed of light, the trip would still last 4.25 years. At airline speeds, it would be 5 million years. The scale difference is so extreme that our minds rebel at processing it. Light is unimaginably fast, yet the universe is unimaginably vast. Those two facts conspire to create a prison made of emptiness and time. Our brains did not evolve for this. We are built to track the trajectory of a spear or the coming of winter, not to contemplate journeys across gulfs where each kilometre is accompanied by 3 nanoseconds of delay. That mismatch leads to intuition traps. We want to picture starflight as long, in the way a cross-country journey is long. But the correct mental model is that a tiny delay per unit distance, multiplied by incredible distance, becomes a delay beyond any personal or even civilizational time. The 8 minutes it takes sunlight to reach Earth, about 1 astronomical unit, feels trivial. Double that, and the time remains under 20 minutes. Multiply by 268,770, and you begin to understand why the nearest star appears unreachable. For all intents and purposes, the speed of light is not slow. Space is just monstrously large. Our senses and language wrap themselves around the immediate. We describe distances with metaphors of walking or sailing. We talk about a stone's throw, a day's ride, across the ocean. Even when we push into larger scales, we borrow from our daily repertoire. We say, beyond a lifetime, half a world away. None of these expressions are remotely adequate for astronomical separations. A light year is about 9.5 trillion kilometers. The circumference of the Earth is 40,000 kilometers. Light laps our planet 7 times in 1 second. The distance to the Moon is about 1.3 light seconds. The distance to the Sun is 8 light minutes. The next star is 4.25 light years. Multiply the gap from here to the Sun by 50,000 and you get the gap to the nearest star. Suddenly, our metaphors fail. An arrow cannot be scaled up to cross such gulf. A walk cannot be extended to 4 million Earth orbits. The dissonance between our intuitive scale and cosmic scale is part of why the speed of light feels infinite until confronted with numbers. Anthropologists note that early number systems seldom counted beyond a few hundred. The concept of 1,000, let alone a trillion, was unnecessary for hunter-gatherers. When modern people hear a billion, we often replace it with the vague sense of a lot. But there are roughly 100 billion stars in the Milky Way. 100 billion is 100,000 millions. If you spent 1 second counting each star, it would take more than 3,000 years to name them all. When you try to imagine crossing that starfield at the finite speed of light, the numbers become even more alien. Our brain's limited arithmetic isn't a failing, it is a reflection of the niche in which we evolved. We had no need to grasp cosmic distances until the last sliver of our history, when we built telescopes and started sending probes beyond the gravitational hold of our planet. To understand why c matters, you have to let go of a Newtonian picture where velocities add and time is absolute. The constant that defines the cosmic speed limit is not just the speed at which light propagates, it is the fundamental rate at which cause and effect can ripple through the fabric of reality. As Einstein showed in 1905, the laws of physics are the same in all inertial frames, and the speed of light in vacuum is constant for all observers. To preserve those two statements, space and time are not separate, but become space-time, and distances and durations mix when you change frames. In this geometry, c sets a conversion factor between intervals of time and intervals of space. That means c is the ultimate speed for any influence, electromagnetic, gravitational, or information. A Forbes exposition on relativity puts it plainly. There is a maximum speed that can link two events causally. You cannot push on something at one place and have it respond faster than a light signal would travel between those points. That limit is not a technological shortcoming. It is built into the structure of causality itself. When Einstein wrote down the special theory of relativity, he was motivated by the desire to reconcile Maxwell's equations with Newtonian mechanics. Newton assumed that time was absolute and the same for all observers, but Maxwell implied that everyone would measure the same speed for light. These are incompatible unless time itself behaves in unexpected ways. Einstein's radical proposal was that observers moving relative to one another would disagree on the durations between events and the lengths of objects, but would agree on the space-time interval. That interval mixes time and space. S squared equals c squared delta t squared minus delta x squared minus delta y squared minus delta z squared. In this equation, c sets the ratio of time to space units. It converts seconds to meters. Without c, there would be no way to compare time to distance. Moreover, c emerges in other deep constants. The fine structure constant alpha, a dimensionless number describing the strength of electromagnetic interactions, is e squared over 4 pi to exon 0 hc. Here, E is the elementary charge, epsilon 0 the vacuum permittivity, h the reduced Planck constant. The presence of c means the strength of the electromagnetic force depends partly on the speed of light. Similarly, the Planck length, the scale at which quantum gravity becomes important, is the square root of hg/c cubed. Reduce c to a small value, and the Planck length grows. Increase it, and the length shrinks. The constant plays a role in every fundamental theory we have. It is also worth pointing out that c is not the maximum speed of light in all media. Light slows down in water or glass. It travels slower through air than through a vacuum. The constant c refers to light speed in vacuum, but it also applies to gravitational waves, neutrinos, and all massless particles. Even when matter appears to travel faster than light in a medium, like Cherenkov radiation in water, where charged particles outrun light in that medium, nothing is exceeding c in vacuum. Cherenkov light is emitted precisely because the particle outruns the slowed light waves in the water, analogous to a sonic boom when a plane exceeds the speed of sound. The universal limit remains unbroken. The best way to visualize this is with light cones. If you imagine your location at some instant in space-time as the apex of a double cone, the future light cone is the region of space-time you can influence. Its sides are the world lines of hypothetical light signals leaving you in all directions. The past light cone is all the events that could have influenced you. Everything outside both cones is too far away in space and too close in time for a light signal to reach or depart. Einstein Online describes this elegantly. By studying how light propagates, we can determine which events can influence a given event and which cannot. The boundary has the form of a double cone formed by all hypothetical light signals. Events outside this double cone are not just physically distant, they are causally disconnected. They cannot affect you until time passes and light, or any signal, can bridge the gap. The wall of the prison is therefore geometric. It is not made of material, but of the shape of space-time itself. In practice, imagining light cones helps to map your own causal influence. Imagine shining a flashlight straight up. The photons you emit trace lines at 45 degrees on a space-time diagram. 1 unit of time for 1 unit of distance in natural units. Every potential future event that lies inside that cone can be illuminated by your signal. Everything outside cannot be reached without exceeding C. Your past light cone contains all the signals that could have reached you by the present moment. It is why we see starlight from only part of the universe. The rest lies outside our past light cone, because there has not been enough time since the Big Bang for light to arrive from there. The boundary between reachable and unreachable events is not fuzzy. It is as crisp as the rim of a cone. An event slightly outside the cone cannot be influenced no matter what energy you devote to it. This notion has deep implications for our understanding of causality and free will. It means there are facts about the universe we cannot know yet, because their light has not reached us. It also means there are events we can no longer affect, because our signals would arrive too late. In a deterministic sense, the future inside your light cone is still open. Beyond the cone, it is inaccessible. In a more philosophical sense, your life story is one thread in a tapestry woven by countless light cones intersecting. Realizing this invites humility. The choices you make ripple outward at sea, but no faster. You cannot undo or preempt causes beyond your reach, and nothing far away can save you from yourself in real time. Once you adopt the light cone perspective, the world becomes a series of accessible and inaccessible regions, defined by C. The 8-minute gap between the Sun and Earth is the time delay on all influences: solar flares, gravitational changes, the warmth we feel on our faces. The Oort cloud, a sphere of icy bodies encircling the solar system, sits about 2 light-years away. At light speed, a message would take nearly 2 years to arrive. Beyond it lies interstellar space and the local neighbourhood, Proxima Centauri at 4.25 light-years, Barnard's star at 6 light-years, the bright star Vega at 25 light-years. Even our cosmic backyard imposes delays measured in years. The Milky Way, our home galaxy, spans about 100,000 light-years and contains hundreds of billions of stars. To cross from one side to the other at light speed would take 100 millennia, and the local group, our immediate cluster of galaxies, contains roughly 50 to 80 galaxies spread over 10 million light-years. The observable universe, due to cosmic expansion, has a diameter of about 93 billion light-years. There is no plausible propulsion system that could cross such distances within anything like a human lifespan. The prison bars become visible when you look out far enough. Within our own solar system, the differences in communication delay are already noticeable to mission planners. Signals to the Moon take about 1.3 seconds round trip. This makes teleoperating a lunar rover feasible. Communicating with Mars introduces a delay ranging from 6 to 40 minutes, depending on orbital positions, which forces Mars rovers to operate semi-autonomously. New Horizons, when it flew past Pluto, was 5.6 billion kilometers away. Its signals took 4.5 hours to reach Earth. And these are all within our tiny neighbourhood. The outer edge of the Oort cloud, where comets originate, lies tens of thousands of astronomical units away. At light speed, it is a journey of years. Crossing that boundary, truly leaving the solar system, is an undertaking of centuries, even for unmanned probes. Beyond the Oort cloud, space becomes almost unimaginably empty. The distance to Proxima Centauri is so huge that even light, which circles Earth 7 times in a second, takes more than 4 years. Multiply that by 25, and you reach Sirius, the brightest star in our night sky. Multiply again, and you reach the Pleiades. Multiply a few hundred times, and you span our galaxy. The Milky Way's spiral arms harbour around 100 to 400 billion stars. If you could travel at 90% C, you could cross it in 110,000 years from an outside perspective. Your proper time would be shorter due to time dilation, but the galaxy would not wait for you. Meanwhile, the local group of galaxies sits as an island chain within the cosmic ocean. The nearest major galaxy, Andromeda, is 2.5 million light-years away. Light left Andromeda during the Pliocene epoch, when our ancestors were learning to walk upright. We see Andromeda as it was then, not as it is now. The cluster of about 50 to 80 galaxies in the local group spans about 10 million light-years. The Virgo cluster and the broader Laniakea supercluster extend hundreds of millions of light-years. The observable universe, due to cosmic expansion, spans about 93 billion light-years. And beyond that, the universe continues, perhaps infinitely, but receding faster than light because space itself is expanding. Distances on these scales are not just long, they are unreachable in principle for any creature limited by C. When cosmologists talk about the horizon, they mean exactly this: a cosmic light cone boundary beyond which we will never see or influence. Relativity deepens the trap. One of the most famous consequences of special relativity is time dilation. A moving clock runs slow relative to a stationary observer. The equations show that the apparent period between ticks is elongated by a factor 1 over squared root of 1 minus v squared over c squared. A lecture from the University of Illinois summarizes this nicely. Moving rods appear shorter and moving clocks run slower, with the proper time between ticks divided by the Lorentz factor. Another NASA Ask an Astrophysicist page explains that as you travel faster, distances shorten and time slows down. Nothing with mass can reach C, because an object's mass effectively increases, requiring infinite energy to accelerate it. These relationships mean that if you could accelerate near light speed, your subjective travel time to a distant star would shrink drastically. Earthbound observers might see your journey take decades. For you, only years might pass. The twin paradox illustrates this. If one twin travels to a star at relativistic speed and returns, she will have aged less than the twin who stayed on Earth. Relativity offers a cheat, but a personal one. The travelers may outrun time, but cannot outrun the loneliness. The people left behind still experience the full interval. It is worth dwelling on the way relativity warps our intuitive categories. In everyday life, we think of time as a constant flow and space as a fixed stage. Relativity tells us that neither is absolute. Time dilation means your own heartbeat slows relative to a stationary observer as you go faster. Length contraction means the distance between 2 points shrinks from your perspective when you move quickly. The formulas that describe these effects are simple, but their consequences are profound. At 10% C, the Lorentz factor is only about 1.005. You would hardly notice any difference. At 90% C, the factor grows to 2.29. Time for you slows to less than half speed relative to Earth. At 99.999% C, the factor is 223. For every day you experience, more than half a year passes on Earth. The trade-off is energy. To get from 90% to 99.999% C requires more than 10 times more energy. The closer you get to C, the steeper the climb. The Universe Today article emphasizes that inertial mass increases with velocity, making further acceleration harder. And there are practical constraints. Human bodies can tolerate only so much acceleration for so long. Even if you accelerate at 1 gram, you will approach C only after about a year of constant thrust, by which time you will be halfway to wherever you are going, and will need to flip the ship and decelerate. The energy to support this is staggering, far beyond what chemical rockets can provide. Time dilation also has social implications. Imagine a voyage to a star 100 light-years away at 99% C. From the ship's perspective, the trip takes about 14 years. On Earth, more than a century passes. The travelers return to a world changed beyond recognition. The languages they speak might be archaic, their families gone. They will have leapt ahead in their personal timeline, relative to Earth's cultural timeline. Such differences strain any concept of shared history. They might as well have stepped into the future via a time machine. This is not science fiction. It is a logical consequence of the Lorentz transformations and has been tested with high-speed particles and atomic clocks. GPS satellites adjust for both special and general relativistic effects. Without those corrections, navigation errors would accumulate quickly. Relativity is not just a theoretical curiosity, it is baked into the technology we use daily. Length contraction, the reciprocal phenomenon, says that objects in the direction of motion shrink by the same factor. To a high-speed traveller, the distance to a target star appears shorter. But this is a perspective effect. It does not mean the star is literally closer for those staying behind. And both effects have a cost. As a craft's speed increases, its kinetic energy climbs steeply. Energy scales with the Lorentz factor. A Universe Today article on relativistic travel and the Fermi paradox quotes researchers explaining that as velocity approaches c, inertial mass increases. Achieving even a small fraction of c demands enormous propellant and energy. The energy required to maintain acceleration is far above the rest energy of the vessel. The crew would also be subject to severe stresses from continuous acceleration and deceleration. To reach 20% of the speed of light, a craft must accelerate for years, and at that speed, a round trip to Proxima Centauri would take more than 40 years in Earth time. Within the ship, only about 10 years would pass. The twin paradox becomes real, but it is no solution for shared journeys because time dilation splits the experiences of the travelers and those who watch them depart. The cruelest part of the cosmic speed limit is not simply that travel takes a long time. It is that communication across the gulf is delayed by exactly the same factors. Light and radio signals are the same phenomenon. All information you send to a distant world is bound by C. A NASA technical report on the Fermi paradox notes that because of the time lag in interstellar communications, any colony would rapidly develop a culture independent of the civilization that originally settled it. Minutes become years, and decades become millennia. Space.com's Paul Sutter describes the consequences for a near light-speed mission. Messages to Mars take minutes, to the outer planets, hours. To a craft heading for a star system many light-years away, a message will take years to arrive. In scenarios where the ship accelerates continuously at 1g, time dilation means the craft would experience weeks, while Earth experiences years. But relativity creates event horizons. If Earth sends a message too late, the craft will outrun the signal. From the ship's perspective, signals from home will eventually go dark. For the travelers, communications blackout is inevitable. The last message from Earth arrives long after they have reached their destination. The radio lag ensures that across interstellar distances, there can be no real-time conversation, no shared present. Colonies separated by tens or hundreds of light years cannot coordinate politics, culture, or economy. They will drift apart because each will always be living in the other's past. The relativity of simultaneity compounds this communication problem. In Newtonian physics, if two events occur at the same time in one frame, they occur at the same time in all frames. Special relativity says otherwise. Observers moving relative to each other disagree about the order of events that are separated in space. This is not an optical illusion, it is fundamental. The famous pole in barn paradox illustrates this. A runner carrying a pole enters a barn shorter than the pole when the runner is at rest. Because of length contraction, the barn door and back door can momentarily be closed simultaneously in the barn's frame without crushing the pole. In the runner's frame, however, the doors are not closed at the same time. The back door opens before the front door closes. Each frame's physics is internally consistent. Now translate that to interstellar politics. A decision made on Earth and a decision made on a colony light years away cannot be unambiguously ordered. Each world will see its actions as now and the others as in the past, due to the finite speed of signal exchange. Attempting to synchronize their clocks precisely becomes impossible. At best, they can agree on signal protocols and accept delays. The NASA technical report about colonization emphasizes that due to the communication lag, colonies will develop independent cultures. Governance becomes asynchronous. Empires fracture not because of rebellion, but because physical law forbids real-time coordination across cosmic distances. For communication engineers, the numbers are sobering. A message to a craft at Proxima Centauri takes over 4 years one way. If the craft travels at 0.5 c, by the time the message arrives, the craft will be 2 light years further. You cannot ask, "How is everything right now?" because by the time you get an answer, 8 to 9 years have passed. Space.com's analysis of communication with near-light-speed spacecraft shows that there are even scenarios where a message sent too late never catches up. At high acceleration, the craft can outrun the radio waves, leaving Earth's transmissions forever behind. Conversely, all messages sent from the craft to Earth will arrive long after they are relevant. Engineers designing a mission to Mars already grapple with how to handle minutes-long delays. An interstellar mission must plan for decades-long delays, if not complete autonomy. The same logic applies to any interstellar civilization. Without faster-than-light communication, governance and shared culture degrade naturally with distance and time. This communication barrier becomes a cultural prison. A civilization could theoretically expand across the galaxy if it had millions of years, sending probes or ships that travel at a significant fraction of c. But once a colony is established, the homeworld cannot govern it in any meaningful way. The NASA report notes that because of the communication lag, each colony will quickly become independent. That independence would not be a rebellion, but a necessity. The only way to maintain a cohesive culture across light-year gaps would be to slow down time itself. But you cannot slow the universe for everyone. Relativistic time dilation helps the travelers, but not the rest. Thus, the speed of light limits not just travel, but the possibility of a single, unified galactic empire. The Fermi paradox, the absence of evidence for extraterrestrial visitations, may in part reflect this barrier. Universe Today remarks that faster-than-light travel is simply not possible unless our understanding of physics is radically incomplete. To accelerate even to 20% of c would require vessels of immense size and fuel, and expose crews to decades of acceleration and deceleration. The challenges of high acceleration and energy supply make interstellar empires improbable. Advanced civilizations might still colonize, but the cost and time reduce their desire or ability to broadcast to us. Relativity does offer its own twisted mercy. Time dilation allows a personal escape from long journeys. The Earth Sky article summarizing a NASA video notes that if you travel near light speed, you will not just feel younger when you return, you will actually be younger compared to friends left behind. Subjective durations shrink. If you accelerate at one gravity halfway to the galactic center and decelerate the rest of the way, you could, in principle, traverse tens of thousands of light years within a human lifetime of proper time. But tens of thousands of years pass on Earth in the meantime. The travelers cannot bring their loved ones with them, because by the time they come back, those loved ones are long dead, and civilizations have risen and fallen. This weird mercy is thus a deeply personal affair. It provides a way to see the universe, but not a way to share it. Humanity has long fantasized about circumventing the speed limit entirely. Science fiction offers warp drives, hyperdrives, and wormholes, mechanisms that would effectively bypass the light barrier by bending space-time or creating shortcuts. The allure of such devices is obvious. They promise a universe where distances do not matter. But there is a price for cheating causality. A Virginia Tech relativity lecture lays out a simple thought experiment. If objects or signals could travel faster than light, you could shoot an arrow that would arrive at a target before you fired it. Messages could be received before they were sent. Cause and effect would be scrambled. To preserve causality, relativity forbids superluminal motion. That is why c is a cosmic speed limit, not merely a technology limit. Any supposed breakthrough must face this fact. Nevertheless, physicists have explored exotic solutions within general relativity that appear to permit effective faster-than-light travel by manipulating spacetime itself. Miguel Alcubierre's 1994 warp drive solution describes a bubble of spacetime contracted in front of a ship and expanded behind it. Inside the bubble, the ship is at rest, so relativity is not violated locally. From the outside, it appears to move faster than light. But the solution requires matter with negative energy density, something not found in nature. A Space.com article explains that the Alcubierre drive requires exotic negative energy. A more recent model suggests a warp drive might not need negative energy, but would only allow very high but subluminal speeds, and still requires enormous energies. In other words, the best theoretical advances do not open a path to light-breaking travel, they simply refine the boundaries. The human imagination naturally gravitates toward loopholes. Science fiction is full of hyperspace routes, warp factors, and jump points, because narrative needs motion to connect characters and plot lines. In everyday storytelling, we compress distances to maintain emotional contact. Fast travel keeps characters in the same temporal frame. In physical reality, there is no such convenience. That is why authors invent subspace communications or quantum entanglement messaging, despite quantum mechanics forbidding faster-than-light signaling. The yearning for FTL reveals our discomfort with separation and delay. It also speaks to a deep part of us that wants the universe to be unified and reachable. When physicists entertain the possibility of FTL within general relativity, they are careful to respect the local speed limit. Solutions like the Alcubierre drive do not move the ship through space faster than c, they move space itself. In effect, the metric is manipulated so that the distance between the origin and destination shrinks. Conceptually, it is as if you put 2 points on a sheet of paper and fold the paper so the points touch. You then poke your pencil through, creating a wormhole or bridge. The path through the sheet is shorter than going across the surface. But doing this to space-time requires energy densities that, in our current understanding, are unphysical. Negative energy appears in quantum field theory in tiny vacuum fluctuations, but harnessing it macroscopically would violate other energy conditions. Some speculative proposals rely on exotic matter with negative mass, which would accelerate in the opposite direction of a force. Such matter has never been observed. The Space.com article about wormholes notes that Kip Thorne proposed negative mass to stabilize a wormhole, but that we have no evidence such material exists. Even if exotic matter could exist, the amounts required for a traversable wormhole are astronomical. More recent warp drive proposals try to sidestep the negative energy requirement by altering the shape of the warp bubble. By making the bubble a finite thickness and changing its profile, the energy density becomes positive, but the effective speed remains less than light. These solutions are interesting mathematical exercises, but they defeat the purpose of a warp drive. If the speed remains subluminal, the warp adds complexity without solving the problem. More importantly, these designs require energy densities comparable to the mass energy of planets or stars. To warp spacetime on macroscopic scales is to tap into gravitational energies far beyond our capability. There is also the issue of Hawking radiation and stability. Some analyses suggest that any warp bubble would collapse or produce catastrophic radiation at its boundaries. The dream remains firmly theoretical. In popular discussions of FTL, quantum entanglement often comes up as a loophole. Entangled particles have correlated properties regardless of distance. Measuring one instantly determines the state of the other. But this correlation cannot be used to send a message faster than light. The outcome of the measurement is random. You cannot choose it. Only when you later compare results via a classical channel, limited by C, can you see the correlation. Entanglement is therefore not a telephone. Experiments with quantum teleportation demonstrate the instantaneous transfer of quantum states, but they also require classical communication to complete the protocol. The speed of light remains unbroken. The rules of the cosmic prison are again affirmed. Another approach to circumventing distance is to exploit cosmic expansion. Galaxies recede from each other because space itself stretches. At great distances, recession velocities exceed c. However, this does not violate special relativity, because the galaxies are not moving through space faster than light. Space itself is expanding. Some cosmologists have speculated about using this expansion to hitchhike. If you build a ring of massive objects, perhaps you could create a region of expanding space behind you and contracting space in front, mimicking a warp drive. But this too demands exotic configurations of energy and matter. At present, it is beyond our engineering, and may be beyond what is physically permissible. The universe seems consistent in its refusal to allow information to outrun C. All of this does not mean the dream of FTL is foolish. It is a powerful narrative device, and a fertile ground for theoretical exploration. Thinking about what a warp drive or wormhole would require has led physicists to investigate the energy conditions of general relativity, the behavior of quantum fields in curved spacetime, and the interplay between gravity and quantum mechanics. In that sense, the dream pushes science forward, but the consensus remains that, within our current understanding of physics, there is no way to achieve superluminal communication or travel without violating causality. The cosmic prison stands firm. Wormholes are another popular idea. These hypothetical tunnels through space-time appear in solutions to Einstein's equations, but for a wormhole to remain open and stable, matter with negative mass or energy is needed. An article from The Conversation, published on space.com, explains that Kip Thorne argued a wormhole would require negative mass matter to hold it open, something we have never observed and do not know how to produce. The exotic matter would push normal matter away, preventing collapse, but there is no evidence such substance exists. Without such scaffolding, a wormhole would pinch off as soon as it formed, or collapse into a black hole. The constraints of general relativity therefore haunt our dreams of shortcuts. We can conceive of them mathematically, but not physically. Because nature offers no free lunch, the only cheats available are those provided by relativity itself. Generational ships accept the prison and attempt to outlast it. Universe Today's discussion of Project Hyperion notes that there are two realistic options for sending humans to exoplanets: develop propulsion capable of relativistic speeds, or build self-sustaining generation ships. The latter would be massive starships, hundreds of meters long, designed to support hundreds or thousands of people over centuries. To maintain genetic diversity, simulations show a minimum initial crew of around 98, supplemented by a cryogenic bank of gametes and embryos. The vessels would have to be largely closed ecosystems, with artificial land for agriculture. One concept calls for 450 square meters of farmable area within a ship 320 meters long and 224 meters in radius. Their life support systems would rely on bioregenerative loops, recycling air, water, and nutrients, and the social systems would need to handle centuries of isolation. Generational ships do not beat the speed of light, they make peace with it. They turn the journey into a home, accepting that those who arrive will not be those who left. Another strategy is to reduce the time experienced by travelers via hibernation or suspended animation. Studies of animal torpor and medically induced hypothermia suggest it may one day be possible to slow human metabolism enough to sleep through decades. An astronomy magazine article notes that if astronauts could slow their metabolic rate drastically, they could sleep through long voyages. Hibernation would reduce resource consumption and radiation exposure. But the article also emphasizes that many technical and ethical challenges remain. Induced hypothermia is used only for brief medical procedures today. Even if perfected, hibernation is not a solution to the light speed barrier. It merely mitigates the subjective boredom of long voyages. We can also outsource the journey to machines. Robotic probes do not need life support and can travel for centuries. Self-replicating von Neumann probes could, in principle, spread throughout the galaxy, pausing at suitable systems to harvest resources and copy themselves. The generation time for such probes might still be limited by the speed of light, but could eventually fill the galaxy with their descendants. Yet, even that scenario does not give a civilization a shared present. Each probe would operate in isolation, with command signals and information exchanges slowed by interstellar delays. In the NASA report on percolation theory and the Fermi paradox, colonizing cultures can spread, but they remain separate clusters. Communication delays ensure that each cluster forms its own culture. The cosmic prison fosters divergence. Another vision of the future involves post-biological travelers, artificial intelligences, or consciousness uploaded into machines. An AI can handle long delays and operate autonomously, adjusting to new environments without immediate oversight. It can hibernate or slow its internal clock to reduce subjective time. But again, the light barrier remains. The AI cannot send a signal faster than C. It may travel far, but cannot bring the rest of us along in real time. The cosmic speed limit also shapes our hopes for interstellar communication. Even if we do not travel physically, we might dream of exchanging information with other civilizations. Radio waves propagate at sea, so a message to a planet 100 light-years away takes a century to arrive. Any reply takes another century. The conversation becomes generational. Paul Sutter points out that a near light-speed spacecraft would stop receiving messages from Earth after a certain point, and would only learn about events on Earth when it decelerated and allowed the signals to catch up. Likewise, Earth would not know about the ship's progress until it had nearly arrived. The simple act of conversation across interstellar distances becomes a slow exchange of recorded history. The prisoners shout across a vast yard, hearing only echoes from the past. When we step back, the cosmic speed limit emerges as a cosmic filter. The Fermi paradox asks, given the vast number of stars and planets, why have we not been contacted? One answer is that physics imposes a strict signal horizon. Even if technologically advanced civilizations exist, their communication bubbles expand at the speed of light. Our own transmissions have been leaking into space for about a century. They have reached stars roughly 100 light-years away. The Milky Way is 100,000 light-years across. A spherical bubble 100 light-years in radius is tiny compared to the galaxy. Meanwhile, radio signals weaken with distance. Interstellar noise and cosmic expansion further degrade them. It is possible that there is a symphony of cultures out there, each broadcasting within its local bubble and never hearing the others because the signals disperse or are absorbed by interstellar gas. The cosmic prison isolates not only individuals, but entire species. The Fermi paradox is often framed as a critique of our expectations, rather than a genuine contradiction. It asks, if the galaxy is filled with billions of potentially habitable planets and has existed for billions of years, why have we not been visited or heard from aliens? Some responses focus on the rarity of life or intelligence, the fragility of civilization, or the possibility that advanced beings choose not to explore. But the cosmic prison offers a less anthropocentric answer. Even if there are thousands of intelligent civilizations, their ability to interact is limited by C. Their radio bubbles expand at light speed, and unless they overlap, they never exchange messages. Their physical probes crawl slowly outward. Their generational ships take millennia. The NASA percolation model treats colonization as a probability problem. Each colony has a chance P to produce another colonizing civilization. Below a critical probability PC, colonization results in finite clusters, separated by non-colonizing societies. Above PC, clusters grow large but still leave voids. Because each colony becomes independent due to communication lag, colonization is not a single coherent wave, but a series of pockets. That means the absence of visitors to our corner is not surprising. We may simply be in a region of the galaxy that has not yet been reached, or that was settled long ago by a culture that chose not to expand further. Universe Today points out that even if civilizations develop relativistic technology, the timescales are daunting. A Type 2 civilization harnessing the energy of its star might send out probes or starships, but those ventures would take tens of thousands or millions of years to cross the galaxy. During that time, the civilization might change, decline, or redirect its efforts inward. Frank Drake's famous equation factors in the average lifetime of technological civilizations. If L, the length of time such a civilization broadcasts, is shorter than the time it takes signals to cross the galaxy, then the overlap of communication windows is small. Dr. Rebecca Charbonneau notes that Drake considered L the most important parameter because our ability to communicate depends on civilizations surviving long enough to hear each other. The speed of light thus acts as a filter in time as well as space. It spreads out the call and reduces the chance of overlapping answers. Physical bars can sometimes be bent with force or cunning. A prison of causality cannot. Attempts to break it lead to paradoxes. The Virginia Tech lecture shows that if you allow faster-than-light travel, cause can follow effect. You could send a message that arrives before it is sent. Physics, as we know it, cannot allow such loops because they undermine the reliability of predictions. Even the most exotic proposals still require forms of matter we do not observe or energies beyond comprehension. The cosmic prison is not a human construct, but a property of the universe. It is why galaxies, stars, and atoms exist in the first place. If information could move infinitely fast, radiation would instantly homogenize energy. Stars could not form stable structures, and perhaps the universe would be unrecognizable. Reluctant acceptance of the prison reveals a different kind of freedom. Boundaries give form. The speed of light allows causality to unfold in an orderly way. It allows energy to propagate gradually, giving stars lifetimes of billions of years. It allows chemical processes to occur at rates amenable to life. Without C, there is no life as we know it. The same constant that prevents us from hopping to the Andromeda Galaxy gives us the warmth of sunlight and the stability of molecules. In that sense, our cage is also our home. The wall we can't cross is the wall that kept us safe long enough to ponder it. This theme, that constraints create stability, recurs across science. The finite speed of propagation ensures that disturbances cannot instantly tear apart matter. The sun's core produces energy that takes thousands of years to migrate to the surface because photons scatter repeatedly. This slow diffusion is why the sun shines steadily for billions of years. The gravitational tug from a stellar explosion 50 light-years away will not impact Earth for 5 decades. Our atmosphere is heated by sunlight that left the sun 8 minutes ago, not by instantaneous changes. Earth's magnetic field deflects charged particles from solar storms, giving us time to brace for their arrival. If signals were instantaneous, the cosmos would be more violent. The speed of light acts like a damping constant in a cosmic orchestra. Without it, or with a much larger or smaller value, stars might burn out quickly or never form. Molecules might not hold together. Life might not emerge. Appreciating the cosmic prison as a gift requires a shift in perspective. You can look at a wall and see confinement, or you can see that within those walls there is room to build a home. The Earth is a haven, not in spite of the speed limit, but because of it. Light's finite speed allows energy gradients to exist long enough for life to exploit them. It allows the universe to have a history, a sequence of events that are locally connected instead of an instantaneous equilibrium. When we talk about the view, we mean more than the aesthetic beauty of a night sky. We mean the ability to perceive stars as they were, and to infer physical laws from their light. Our ability to know the universe emerges from the same causal structure that binds us. So what futures remain for beings like us? Slow and steady ones. Robotic probes crawling outward at fractions of light speed, sending back data over decades. Possibly a handful of generation ships, launched by a mature civilization, carrying communities willing to sacrifice immediate connection for the dream of new worlds. Maybe hibernating astronauts, sleeping through centuries. Perhaps eventual descendants who are partly machine and can handle isolation and delay. Each path acknowledges that the universe is not made for our convenience. It is vast, expanding, and indifferent. Our ingenuity is real, but it must play within the rules. The awareness of the cosmic prison also reshapes our sense of time. In a universe where signals propagate at finite speed, there is no absolute now. Two events separated by sufficient distance cannot agree on simultaneity. Relativity teaches that simultaneity is relative. Observers moving at different velocities disagree about which events are simultaneous. In cosmic terms, there is no single present moment for the galaxy. Every time we look up at the stars, we see ancient light. We see Andromeda as it was more than 2 million years ago. The light from the most distant galaxies shows them as they were billions of years ago. Our present is stitched together from countless pasts. Realizing this can produce a quiet awe and a subtle dread. Our stories, our empires, our tragedies occur on a grain of dust in one corner of a cosmic timescape that we cannot synchronize. The prison walls are not just in space, but in time. If this feels oppressive, remember that meaning does not depend on being everywhere at once. The universe is too large to ever be fully experienced by any one being or civilization. Yet within our light cone, there is richness. Earth's biosphere, the orbit of the moon, the gravitational dance of planets, the possibility of future homes around nearby stars. Our species has existed for a few 100,000 years, our civilization for a few thousand. In cosmic terms, we are infants. The speed of light may keep us from conquering the galaxy, but it does not prevent us from exploring, learning, creating, and connecting within our bubble. There is beauty in the local. When Voyager 1 eventually leaves the solar system's gravitational influence, something that will take tens of thousands of years, it will carry a record of our music and greetings from our time to unknown listeners. It will be a message to the void. Whether anyone ever hears it is uncertain, but the act of sending it was itself a triumph. There is comfort in knowing that cosmic limitations apply to everyone. The same speed limit that binds us binds any other civilization. We are all subject to the same causal network. If aliens look up at their night sky, they too see ancient light. They too wonder about their neighbours and send out signals that dissipate into the void. Our loneliness is not unique. It is a property of the cosmos. Recognizing that shared constraint can foster solidarity with hypothetical others. We are all prisoners of the same geometry. Living with the speed limit invites us to focus on depth rather than breadth. We may never visit galaxies beyond the local group, but we can explore our solar system in exquisite detail. We can study the planets, moons, and asteroids up close, send probes to the Kuiper Belt and beyond, and build telescopes that peer into the early universe. We can cultivate relationships with future colonies, even if messages take years. We can create art, music, and ideas that travel slower than light, but still outlive us. We can become good stewards of our own planet, and consider whether and when to venture further. Limitation breeds creativity. The cosmic wall makes us think carefully about what we value enough to send across generations. Perhaps the prison metaphor is too harsh. A prison is imposed by an external authority. The cosmic speed limit simply is. It does not punish, it defines. A more fitting image might be an island. We live on an island of space-time, with shores delineated by light. The ocean beyond is not hostile, it is simply unreachable, except by the ripples of radiation we send and receive. On our island, we build cultures, languages, sciences, and dreams. We look across the sea and see other islands shimmering in the haze. We do not know if they are inhabited. We send out bottles with messages, knowing the currents are slow. We may never receive a reply. Still, we send them, not because we expect rescue, but because the act of reaching out is itself an assertion of being alive. The wall stands, the sea is vast, and yet there is solace in knowing we are part of a larger archipelago of light cones, each with its own story, unfolding at its own pace. In this light, the speed of light becomes a companion rather than a jailer. It gives rhythm to the cosmos. It sets the tempo of supernovae and the heartbeat of galaxies. It ensures that cause precedes effect and that history has direction. When we accept that we cannot outrun it, we become free to appreciate the beauty within its bounds. The cosmic prison is not made of steel. It is made of too late, as one motif suggests. But within that too late, there is just in time, the moment of existence where we can reflect, explore, and share. A slow, spacious understanding replaces the frantic desire to be everywhere at once. There is a quiet intensity in this acceptance, awe at the night sky, resignation to our limits, curiosity about what we can still do. The truth, once seen, cannot be unseen, and that truth can inspire not despair, but a deeper love for our finite, local place in the universe. In the end, the speed of light is both a prison and a promise. It confines us to a finite region, forcing humility, patience, and acceptance. It also underpins the very structures that make life possible. The wall is there, unyielding, woven into the fabric of reality. We may dream of warp drives and wormholes. We may build generation ships and self-replicating probes, but we cannot escape the truth that no matter how brilliant we become, most of the universe will always lie beyond our causal reach. There is a strange calm in embracing this. We are small. We are brilliant. We are trapped in our local bubble of space-time. And yet, inside this boundary, we are free to think, to love, to explore, to send out messages into the dark, and to find meaning in our shared journey around an unremarkable star. The prison is real, so is the view. The night sky over our world is silent. If you live far from city lights and let your eyes adjust, you see the splash of the Milky Way, millions upon millions of suns forming a diffuse band across the darkness. For the most part, nothing seems to move. We expect fireworks, visitors, a cosmic throng. Instead, we are greeted with emptiness. Somewhere in that emptiness, there are radio pulses, supernovas, the occasional whisper of a comet or asteroid passing through. But there is nothing that looks like a parade of distant spacecraft, no obvious beacon announcing, "We are here." There is simply deep quiet. To many people, that quietness feels ominous. There is a fear that behind the silence lies danger. Perhaps the cosmos is a battleground, and the first to speak is the first to be silenced. This story begins by turning that assumption on its head. What if the silence is not an absence of voices, but the result of deliberate restraint? What if the cosmos is full of minds that have chosen to go quiet because they understand the weight of their actions? Sitting with that possibility requires a different mood than our usual science fiction fantasies. This exploration will be slow and meditative, moving through science and philosophy, setting aside the compulsive urgency that normally accompanies discussions about alien life. We will proceed like walking through a library in the dark, stopping at shelves to examine ideas about survival, cooperation, ethics, and the long arc of civilizations. Our first stop is our own intuition. When the idea of aliens comes up, human stories almost automatically paint them as monsters or conquerors. That instinct is not merely because Hollywood producers enjoy conflict. Evolution has wired our nervous systems to be highly sensitive to threats. Our ancestors faced predators, disease, venomous creatures, hostile rivals, starvation, and unpredictable environmental hazards. Those who erred on the side of caution, who ran away at the faint rustle in the grass, or avoided the dark cave, left more descendants. Our brains are full of fear systems aimed at dangers ranging from animals to social rejection. When we imagine unknown beings, our minds naturally populate them with our worst fears. We extrapolate from our own history of colonial conquest, warfare, and oppression. Science fiction frequently projects our aggressive tendencies onto hypothetical aliens, because that makes for drama, and because it feels realistic, based on human behavior. Even our thought experiments often default to a survival mindset, in which competition is the only game in town. Recognizing this bias helps us see that the expectation of hostile aliens is not a rational deduction, but an emotional reflex. Our species carries the scars of conflicts and catastrophes, and therefore tends to imagine the universe as a place where conflict is the default. Changing that default requires acknowledging the bias, without dismissing the reality of danger. We begin by asking what kinds of civilizations could plausibly reach the stars, and how they would have to behave to survive long enough to do so. To grasp the scale of this question, we revisit the Fermi paradox. In the 1950s, physicist Enrico Fermi asked his famous question, "Where is everybody?" The reasoning behind the paradox is simple. Our galaxy contains hundreds of billions of stars, many similar to the Sun. If even a tiny fraction of those stars host planets with intelligent life, and if those intelligences develop modest spacefaring technology, then over tens of millions of years, they should be able to travel across the galaxy. Yet we see no evidence of their presence. Something is missing. Possible explanations range from intelligent life being rare to civilizations destroying themselves before they spread. One proposal suggests that advanced civilizations deliberately avoid contact. Here we explore a specific possibility. Perhaps the filter that determines which civilizations survive long enough to explore the galaxy is ethical maturity. Maybe by the time a civilization can leave its star system, it has already overcome its own capacity for self-annihilation. The assumption that violent expansion is inevitable is challenged by simple economics and game theory. War is devastating and expensive. It destroys infrastructure, destabilizes societies, and consumes resources that could otherwise support well-being and development. Competitive approaches tend to increase animosity and erode trust, while cooperative approaches build stability and mutual benefit. In repeated interactions, cooperation often produces better long-term outcomes than unchecked aggression. If this holds for human groups, it likely applies to extraterrestrial intelligences as well. In a cosmic context, the costs of interstellar war, in energy, time, and risk, would be astronomical. A technologically mature species might find that cooperation and knowledge exchange are far more profitable than conquest. When your time horizon spans millennia, short-term gains from plunder look trivial compared to the benefits of stable partnerships. Survival into deep time also requires managing existential risks. Civilizations face threats that can cause harm on a planetary scale: environmental collapse, nuclear war, pandemics, asteroid impacts, and runaway technologies. Species that fail to control their own destructive capacities simply do not persist long enough to build starships. Any civilization that reaches interstellar capability must have learned restraint, coordination, and long-term planning. Humanity is currently struggling with this challenge. We are capable of extraordinary cooperation and extraordinary destruction. The lesson is sobering but clear. Survival demands institutions and cultural norms that discourage catastrophic behavior. It is plausible that alien civilizations face similar trials, and that the ones who endure are those who master cooperation, risk management, and restraint. From this perspective, ethics can be seen as a form of civilizational natural selection. Ethical systems are not abstract ideals. They are strategies for aligning behavior with long-term flourishing. Some emphasize weighing outcomes and minimizing harm. Others focus on protecting rights and treating individuals as ends rather than means. Long-term thinking asks us to consider the well-being of future generations. For a civilization to coordinate across centuries, it must care about people not yet born, and perhaps not even of the same biological form. Benevolence, in this sense, is not naive optimism, but a rational survival strategy. Cooperation also follows a cold logic. War creates feedback loops of retaliation. Collaboration builds networks that endure. Even rivals often share interests and must cooperate to avoid mutual destruction. A mature civilization might apply these lessons on a cosmic scale, designing systems that make aggression unattractive and reward mutual respect. Benevolence then becomes a form of enlightened self-interest. If ethical maturity supports survival, then benevolent aliens become plausible. But what about the great silence? One way to reconcile benevolence with absence is non-interference. Intervening in a young society carries enormous risk. Power asymmetries can destroy cultures, create dependency, or enable catastrophic misuse of technology. Silence, in this view, is not indifference, but caution. A civilization that values long-term flourishing may choose to wait rather than interfere. There are many possible paths to ethical maturity. Some civilizations may arrive there through philosophy and rational discourse. Others may cultivate compassion through contemplative practices that reduce ego and expand empathy. Compassion, like any skill, can be trained and embedded into culture. Still others may move beyond biological limitations altogether, becoming post-biological or digital minds. Freed from scarcity, fear of death, or competition for territory, such beings might find cooperation far more natural. These paths are speculative, but they widen our imagination beyond the assumption that intelligence inevitably leads to domination. The speed of light adds another layer of restraint. Interstellar communication is slow. Conversations unfold over years or centuries. There is no shared present, no common now. Civilizations separated by light years cannot easily form unified political structures or empires. They fragment into local cultures, each evolving on its own timeline. This physical limit creates a kind of psychological prison. Even if we could travel to the stars, those who leave would be leaving our present forever. Seen this way, the silence of the cosmos may be an invitation rather than a threat. If survival into deep time requires ethical maturity, then the path to any future cosmic community begins at home. We can choose cooperation over conquest, stewardship over exploitation, restraint over excess. When you look up at the quiet stars, imagine not a hostile void, but a universe shaped by patience. The silence may be full of watchers, each in their own bubble of causality, hoping that we learn to choose care. The universe may not be hostile, it may be mature, and that maturity, built slowly over eons, may be what truly binds a cosmic community together. In the early 20th century, physicists began noticing that the familiar rules of classical mechanics were failing them. Light, which Maxwell had described as a continuous wave, turned out to arrive in discrete packets of energy called photons. Matter, which Newton described as localized particles following smooth trajectories, began to behave in strange, wave-like ways. This was the beginning of the quantum revolution. The core insight was that at the smallest scales, nature is quantized. Energy comes in discrete chunks, and particles exhibit interference patterns like waves. Even when we fire individual photons, one at a time through a double-slit apparatus, an interference pattern emerges on the screen over time, implying that each photon somehow traverses both paths and interferes with itself. When we try to determine which slit a photon passes through, the interference pattern fades. The more information we obtain about the photon's path, the less pronounced the wave pattern becomes. This dual character of light and matter, behaving as both particle and wave, is called wave-particle duality. Quantum mechanics invites us to rethink the very nature of a physical state. In the classical world, an object has a definite position and velocity at all times. In the quantum world, the best description of a system is a wave function, an abstract mathematical object that tells us the probability amplitude for each possible outcome. Before we measure, a quantum system can exist in superposition, multiple seemingly contradictory possibilities at once. An electron in an atom isn't orbiting like a planet around a star. Rather, its wave function spreads throughout space, encoding the probability of finding the electron at various locations. Superposition allows quantum bits, or qubits, to be 0 and 1 simultaneously, enabling quantum computers to explore many possible states at once. The NIST quantum primer likens superposition to multiple overlapping musical notes. When several frequencies are played simultaneously, the resulting tone contains all of them until we listen carefully to pick out one. One of the most startling features of quantum mechanics is that measurement disturbs the system. Heisenberg's uncertainty principle quantifies this by stating that certain pairs of properties, such as position and momentum, cannot both be known arbitrarily well. If we determine an electron's position very precisely, its momentum becomes highly uncertain, and vice versa. The intrinsic quantum uncertainty also means that a particle bound to a potential can never be completely at rest. Even a ball attached to a spring has a minimum energy due to zero-point motion, a direct consequence of the uncertainty principle. Physicist Matt Strassler notes that the zero-point energy of a simple oscillator is half a quantum of energy, and this energy is always present. Because of the uncertainty principle, the electron in the ground state of an atom has a non-zero kinetic energy and cannot collapse into the nucleus. Planck's constant, denoted h, sets the scale of quantum effects. It tells us how small these quanta of energy are. The NIST metrology guide emphasizes that energy is exchanged in discrete chunks, and h defines the size of those quanta. Its exact value, 6.626070, 15 times 10 to the 3 billion joules, now defines the kilogram and other SI units. Planck's constant is tiny compared to everyday energies, which is why quantum effects are usually hidden in our macroscopic world. Yet, at atomic and subatomic scales, h controls everything: how electrons occupy discrete energy levels, how photons carry energy proportional to their frequency, and how the phase of a wave function evolves in time. Quantum mechanics also reveals that particles can tunnel through energy barriers they classically should not cross. A particle described by a wave function does not vanish abruptly at a barrier. Its amplitude decays exponentially inside the barrier, leaving a finite probability of appearing on the other side. A textbook example is nuclear alpha decay, where an alpha particle escapes the nucleus by tunneling through the nuclear potential wall. OpenStax notes that if a wave packet is wider than a barrier, there is a non-zero chance of finding the particle beyond it, a phenomenon first analysed by Friedrich Hund and later used by George Gamow to explain alpha decay. Quantum tunneling underpins modern technologies such as scanning tunneling microscopes and tunnel diodes. The act of measurement plays a subtle role in quantum theory. Early interpretations suggested that consciousness causes collapse, leading to philosophical puzzles. Contemporary physics emphasizes that when a quantum system interacts with a measuring apparatus or the environment, information leaks out and the coherence between different components of the wave function is lost. The Caltech Science Exchange clarifies that an electron behaves like a wave when left unobserved, but measurement, an interaction with the environment, causes the wave function to collapse or decohere, so that the electron behaves like a particle with a definite position. Decoherence explains why we don't perceive macroscopic superpositions in everyday life. Environmental interactions rapidly destroy interference between different macroscopic states. The quantum world also defies locality. Entangled particles can exhibit correlations that cannot be explained by local hidden variables. When two photons are entangled, measuring the polarization of one instantaneously determines the polarization of the other, even if they are light years apart. The EPR paradox, proposed by Einstein, Podolsky, and Rosen, suggested that quantum mechanics might be incomplete because it predicts such spooky action at a distance. John Bell proved that any local hidden variable theory must satisfy certain inequalities. Nobel Prize press materials explain that experiments by John Clauser, Alan Aspect, and Anton Zeilinger violated Bell's inequalities, showing that the correlations predicted by quantum mechanics exceed what any local theory can produce. These experiments confirm that entangled particles behave as a single, non-local system, and that the universe is fundamentally non-local. Entanglement is not just a philosophical curiosity, it is a resource for quantum information. The NIST primer describes entangled photons used in quantum key distribution, where the correlated outcomes of measurements provide secret cryptographic keys that are secure against eavesdroppers. Entanglement also enables quantum teleportation. Northwestern University researchers demonstrated that performing a joint measurement on two photons, one carrying a quantum state and one entangled with a distant partner, transfers the quantum state to the distant photon without sending any physical particle across the channel. BBC Science Focus summarizes that quantum teleportation relies on entanglement and allows information to be transferred without the particles traveling the distance. Teleportation experiments use entangled photons distributed through fiber optics. After the joint measurement, classical communication conveys the result to complete the transfer, consistent with relativity. The menagerie of quantum particles is rich and organized. Matter is composed of fermions, particles with half-integer spin that obey the Pauli exclusion principle. These include leptons, such as electrons and neutrinos, and quarks that combine into protons and neutrons. Force carriers are bosons, particles with integer spin that can occupy the same quantum state. The Department of Energy explains that photons mediate electromagnetism, gluons carry the strong force, and W and Z bosons carry the weak force. The Higgs boson gives mass to quarks, charged leptons, and the W and Z bosons through its interactions. Only up and down quarks and electrons are needed to build all ordinary matter. The Higgs boson itself, discovered in 2012, is the excitation of a pervasive field that permeates space. Brown University describes how interactions with the Higgs field set the masses of quarks, charged leptons, and the massive force carriers. Without this mechanism, these particles would be massless and unable to form atoms. The discovery left many open questions about the Higgs potential and whether the universe could tunnel into a lower state. Antimatter mirrors matter, but with opposite charges. A positron is an anti-electron. When matter and antimatter meet, they annihilate into photons. At CERN's antimatter factory, physicists routinely create anti-atoms. The Science in School article notes that antiparticles occur naturally. For example, the radioactive decay of potassium-40 inside bananas produces positrons. Our bodies generate thousands of antiparticles daily. Observations show that the Big Bang should have produced equal amounts of matter and antimatter, yet our universe is dominated by matter. Understanding the matter-antimatter asymmetry is an active area of research. Virtual particles, those fleeting disturbances that appear in Feynman diagrams, play a subtle role. According to Fermilab physicists, virtual particles are real in the sense that they are temporary fluctuations allowed by the energy-time uncertainty principle. They mediate forces and affect measurable quantities like particle lifetimes. When two charged objects repel each other, we can think of them exchanging virtual photons. In the strong force, nucleons exchange virtual pions. Yukawa proposed in 1935 that protons and neutrons attract by exchanging pions whose mass and lifetime set the range of the force. Because a pion's existence is limited by the uncertainty principle, the strong force acts only over nuclear distances. Experiments later discovered real pions with masses close to Yukawa's prediction. Spin is an intrinsic quantum property unrelated to literal rotation. The Quantum Atlas explains that particles have quantized spin. Fermions have half-integer spins, while bosons have integer spins. The Stern-Gerlach experiment showed that silver atoms passing through a magnetic field split into discrete beams, revealing quantized spin orientations. Because of spin and the Pauli exclusion principle, no two identical fermions can occupy the same quantum state, which shapes the structure of atoms and the periodic table. Spin orientation can be measured by magnetic resonance, a technique used in MRI imaging. Bosons, by contrast, can occupy the same state. This property allows lasers, superconductors, and Bose-Einstein condensates. Antimatter has its mirror as well, the Majorana fermion, predicted by Ettore Majorana, which is its own antiparticle. Scientists have been searching for signatures of these elusive particles, because they may provide robust qubits. A UCLA experiment combined a superconductor with a magnetic topological insulator and observed a quantized zero-bias conductance consistent with Majorana particles. In this context, a Majorana state can be thought of as half an electron. Because it lacks electric charge, it is less sensitive to environmental noise, potentially enabling fault-tolerant topological quantum computing. Our current understanding of particles and forces is encapsulated in the Standard Model, but this framework leaves important questions unanswered. It doesn't include gravity or dark matter, and it cannot explain neutrino masses or the matter-antimatter asymmetry. The search for physics beyond the Standard Model drives experiments like those at the Large Hadron Collider and neutrino detectors. Grand unified theories attempt to merge the strong, weak, and electromagnetic interactions, often predicting new particles or symmetries. At even higher energies, quantum gravity becomes essential. String theory posits that fundamental particles are tiny vibrating strings. Loop quantum gravity suggests space itself has a discrete structure. Both aim to reconcile quantum mechanics with general relativity. Neither has yet produced definitive experimental predictions, but they have stimulated rich mathematics and new ways of thinking about spacetime. Interpretations of quantum mechanics aim to make sense of the mathematical formalism and experimental results. The Copenhagen interpretation, associated with Niels Bohr and Werner Heisenberg, holds that the wave function encodes all possible outcomes and collapses to a particular result upon measurement. The many worlds interpretation proposes that all possible outcomes actually occur in different branches of a multiverse, avoiding collapse but multiplying worlds. Bohmian mechanics, or pilot wave theory, posits that particles have definite positions guided by a pilot wave. The transactional interpretation treats quantum events as handshake-like exchanges between future and past waves. These interpretations yield the same experimental predictions, but differ philosophically. Thought experiments like Schrödinger's cat, placing a cat in a superposition of alive and dead, illustrate the tensions between quantum superposition and classical reality. Wigner's friend raises questions about whether observers themselves can be superposed, and whether consciousness collapses the wave function. While these debates may seem esoteric, they underscore the conceptual richness of quantum theory and its unresolved puzzles. Quantum field theory, QFT, goes beyond the particle picture and describes everything as excitations of underlying fields. According to QFT, the electron is not a point particle floating in empty space, but a ripple in the electron field. Photons are ripples in the electromagnetic field. Quarks are ripples in quark fields. The vacuum is not empty. It is a sea of fluctuating fields. These fluctuations give rise to observable effects. One famous example is the Casimir effect. When two neutral mirrors are placed very close together, some electromagnetic modes cannot fit between them. Scientific American explains that this reduction in vacuum energy density inside, compared with outside, causes a small attraction between the plates. The effect was predicted by Hendrik Casimir in 1948 and measured by Steve Lamoureux in 1996. Calculations of vacuum energy often diverge to infinity, but physicists extract finite, observable differences by subtracting energies at different separations, a technique reminiscent of renormalization. Another vacuum phenomenon is the Lamb shift, a tiny difference in energy levels of hydrogen predicted by quantum electrodynamics and measured by Willis-Lamb. It arises from the interaction of the electron with vacuum fluctuations. Similarly, the Yukawa potential emerges from the exchange of virtual pions. Because the virtual particle's lifetime is limited by the uncertainty principle, the potential falls off exponentially, explaining the short range of the nuclear force. The spin statistics theorem, a deep result of QFT, shows that particles with integer spin, bosons, have symmetric wave functions, and thus can occupy the same state, while particles with half-integer spin, fermions, have antisymmetric wave functions and obey the exclusion principle. These mathematical properties stem from the structure of spacetime and the requirement of relativistic invariance. Quantum technologies harness these phenomena. Quantum computers use qubits that can exist in superposition and be entangled. The NIST article explains that 2 qubits can represent 4 combinations at once, and additional qubits exponentially increase the computational space. Operations are implemented by carefully timed laser pulses or microwave signals. Because measurement collapses the state, quantum algorithms must be designed so that the correct answer has a high probability of being measured. Qubits are fragile. Stray electromagnetic fields or thermal noise can disrupt them, causing decoherence. Different physical platforms, trapped ions, superconducting circuits, semiconducting quantum dots, topological qubits, compete to realize scalable quantum computers. Entanglement is also used in quantum sensing. Entangled states can improve the precision of measurements beyond classical limits. Quantum key distribution already provides provably secure cryptography by detecting any eavesdropping as changes in the correlations of entangled photons. Atomic clocks are a triumph of quantum control. The SI second is defined as 9,192,631,770 periods of the radiation corresponding to the transition between two hyperfine levels of the ground state of a cesium-133 atom. In a cesium beam clock, atoms are heated and sent through a microwave cavity. Each atom has an electron whose spin states have slightly different energies. When microwaves of the resonant frequency flip the electron's spin, detectors count how many atoms change state. A feedback loop tunes the microwave frequency. The measured resonance defines the passage of time. More advanced optical lattice clocks use strontium or ytterbium atoms, achieving even higher precision by operating at optical frequencies. Lasers, which stand for light amplification by stimulated emission of radiation, create coherent beams of light where the waves are in phase. NASA explains that because laser light remains narrow and does not spread out like regular light, it can cut, drill, transmit information, and perform surgery. In a laser, atoms or molecules are pumped into an excited state. When one photon stimulates an excited atom to emit another photon, the emitted photon has the same phase and direction, amplifying the beam. Lasers are essential for optical communications, barcode scanners, gravitational wave detectors, and countless other technologies. Superconductivity arises when certain materials are cooled below a critical temperature and conduct electricity without resistance. Electrons pair up through phonon interactions, forming Cooper pairs that move coherently. The DOE explains that superconductors can carry large currents without energy loss and expel magnetic fields, as seen in the Meissner effect. Superconductors enable MRI magnets, particle accelerator magnets, maglev trains, and quantum bits based on Josephson junctions. Superconductivity is analogous to superfluidity, where liquid helium flows through narrow channels without friction. Nobel laureate Anthony Leggett notes that superfluid helium can climb the walls of a container and exhibits the Hess-Fairbank effect, while superconductors show zero electrical resistance. Both phenomena arise from macroscopic quantum coherence. Scanning tunneling microscopy, STM, uses quantum tunneling to image surfaces at atomic resolution. Harvard's overview describes how a sharp conducting tip is brought very close to a sample. When a bias voltage is applied, electrons tunnel through the vacuum gap. The tunneling current depends on the density of electronic states beneath the tip. By scanning the tip over the sample and measuring the tunneling current, STM can map the surface topography and electronic structure. The technique hinges on the quantum ability of electrons to tunnel through a barrier. Magnetic resonance imaging, MRI, and nuclear magnetic resonance, NMR, exploit the spin of atomic nuclei. Nuclei with odd numbers of protons or neutrons have half-integer spins, making them tiny magnets. King's College London explains that in a magnetic field, these nuclear magnetic moments align and precess at a characteristic Lama frequency. A radio frequency pulse tips the spins out of alignment. As they relax back, they emit a signal that reveals their environment. The energy difference between spin states is small, which is why strong magnetic fields are used. MRI maps the distribution of hydrogen, i.e. water, in the body, while NMR provides information on molecular structure in chemistry and materials science. Quantum dots are artificial atoms, semiconductor structures that confine electrons and holes in all three dimensions. West Virginia University notes that when a confined electron and hole recombine in a quantum dot, a photon is emitted, and the quantum state of the carriers can be manipulated with lasers and fields. Because quantum dots have discrete energy levels, they can act as qubits, emit single photons for quantum communication, and be tuned by size. Their tunable emission colors make them useful for displays and biomedical imaging. Researchers also explore exotic quantum states like Bose-Einstein condensates, BECs. When bosonic atoms are cooled to near absolute zero, their de Broglie wavelengths overlap, and they merge into a single quantum state. Rice University describes how this phenomenon, predicted by Einstein and Bose, creates a superatom, where quantum effects manifest on a macroscopic scale. Because bosons can occupy the same state, their wave functions reinforce one another. Fermions cannot form such a condensate because the Pauli exclusion principle prevents them from sharing a state. Superfluidity extends beyond helium. Leggett explains that superfluids flow without friction and exhibit phenomena like the Hess-Fairbank effect, where a rotating superfluid appears to come to rest. Superfluid helium is used as a coolant for superconducting magnets and detectors. Superfluidity is a manifestation of quantum coherence on a macroscopic scale. All atoms occupy the same quantum state and move in unison. Another exotic state arises in two-dimensional electron systems subject to a strong magnetic field, the quantum Hall effect. NIST reports that when a two-dimensional electron gas is exposed to a large magnetic field, the electrons undergo cyclotron motion and condense into discrete Landau levels. The Hall resistance becomes quantized in units of h pounds e squared. This phenomenon, discovered in 1980, provides a fundamental standard of resistance. The fractional quantum Hall effect, observed in graphene and semiconductor heterostructures, arises from strong interactions that cause electrons to form correlated states with fractional charge. The quantum Hall effect illustrates how topology and magnetism combine to produce robust quantized phenomena. In certain semiconductors, a photon can excite an electron from the valence band to the conduction band, leaving behind a positively charged hole. The electron and hole attract each other and bind into a neutral quasiparticle called an exciton. The National Renewable Energy Laboratory notes that excitons can be controlled and used in quantum computing and optoelectronic devices. Because excitons are neutral, they are less sensitive to electrical noise. In some materials, they can form condensates analogous to BECs. Topological insulators are materials whose interior acts as an insulator, while their surface or edges conduct electricity. The conduction channels are protected by the material's topological properties and cannot be easily removed by disorder. The University of California, Riverside explains that in two-dimensional topological insulators, electrons flow along the edges with little resistance. In three-dimensional topological insulators, surface states conduct while the bulk remains insulating. Because topological protection makes these states robust against scattering, they are promising platforms for quantum computing and spintronics. Materials near a quantum critical point, where two different phases meet at zero temperature, exhibit unusual behavior. SciTech Daily summarizes that in strange metals near such a point, quasiparticles lose their identity and the usual Fermi liquid description fails. The Fermi surface can reconstruct, Planckian timescales emerge, and correlations persist over long distances. Quantum criticality may underlie high-temperature superconductivity and heavy fermion behavior. Studying these systems gives insight into collective quantum phenomena. Another subtle technique is quantum squeezing. Quantum fluctuations impose a trade-off between uncertainties in complementary variables like amplitude and phase. Argonne researchers describe devices called squeezers that reduce uncertainty in one variable at the expense of increased uncertainty in the other. Squeezed light improves the sensitivity of gravitational wave detectors, such as LIGO, and enhances atomic clocks. By preparing a squeeze state of light or atoms, we can surpass the standard quantum limit in precision metrology. The world of exotic particles continues. Majorana fermions have been mentioned. Experiments also seek vial fermions and other quasiparticles like anyons, which obey statistics intermediate between bosons and fermions. In fractional quantum Hall systems, anyons can braid around each other, acquiring fractional phases. Topological quantum computing aims to encode information in such braid statistics to protect it from decoherence. To navigate this complexity, the mathematical formalism of quantum mechanics is essential. At its heart is the Schrödinger equation, which determines how the wave function evolves in time. The Hamiltonian operator encodes the total energy of the system. Eigenvalues and eigenvectors of the Hamiltonian correspond to allowed energy levels and stationary states. Commutation relations express fundamental incompatibilities between observables, such as the position and momentum operators, whose commutator is I. The state space is a Hilbert space, an abstract vector space with an inner product that allows us to calculate probabilities. We often use Dirac's Bra-Ket notation, where the ket psi represents a state and the bra phi represents its dual. The Born rule says that the probability of obtaining a particular measurement outcome is the squared magnitude of the projection of the state onto the measurement eigenstate. Unitary operators describe time evolution and ensure that probability is conserved. Density matrices extend the formalism to statistical mixtures and entangled subsystems. These mathematical tools enable physicists to predict and engineer quantum behaviors in the laboratory. Quantum mechanics raises deep questions about measurement and reality. Decoherence provides a mechanism for the apparent collapse of the wave function. Interactions with the environment entangle the system with countless degrees of freedom, effectively suppressing interference. Yet, decoherence doesn't by itself select a single outcome. It merely explains the loss of coherence. The measurement problem, why we observe definite outcomes at all, remains unresolved. Quantum Darwinism suggests that certain pointer states proliferate their information redundantly into the environment, making them objective. Other approaches involve spontaneous collapse models that modify the Schrödinger equation. These debates continue to inspire experimental tests involving macroscopic superpositions and entangled mechanical resonators. At the interface of quantum mechanics and general relativity, perplexing puzzles arise. Black holes radiate due to quantum effects near the event horizon, a phenomenon predicted by Stephen Hawking. Hawking radiation implies that black holes can evaporate over time, but this leads to the information paradox. Does information about the matter that formed a black hole vanish when the black hole evaporates, violating unitarity? Proposed resolutions include the holographic principle, which suggests that information about the three-dimensional interior of a region is encoded on its two-dimensional boundary. Quantum cosmology tries to describe the early universe when quantum and gravitational effects were both strong. Loop quantum gravity proposes that space is made of discrete loops, preventing singularities. String theory posits extra dimensions and that particles are vibrating strings. It unifies quantum mechanics with gravity at the price of a landscape of possible universes. Entropic gravity theorizes that gravity emerges from thermodynamic principles. None of these ideas has been definitively confirmed, but they highlight the frontier of theoretical physics. Exotic quantum phenomena push our understanding further. Indistinguishability of identical particles means we cannot label electrons. Their wave function is either symmetric or antisymmetric under exchange. In bosons, swapping two particles leaves the wave function unchanged. In fermions, it acquires a minus sign. This simple mathematical property has vast consequences, giving rise to the Pauli exclusion principle and the properties of matter. Heisenberg's microscope thought experiment illustrates the limits of measurement. Attempting to resolve an electron's position with high precision requires high-energy photons that impart momentum to the electron, reinforcing the uncertainty principle. Quantum Darwinism posits that certain stable states proliferate their information through many copies in the environment, making classical reality robust. The Aharonov-Bohm effect shows that even in regions where magnetic and electric fields vanish, the potentials can affect the phase of a charged particle's wave function, causing observable shifts in interference patterns. The quantum Zeno effect demonstrates that frequent measurement can freeze a system's evolution. An unstable nucleus observed continuously can appear never to decay. Richard Feynman's path integral formulation recasts quantum mechanics as a sum over all possible histories. Each path contributes with a phase determined by the action, and interference among histories gives rise to quantum behavior. Delayed choice experiments, like Wheeler's delayed choice quantum eraser, highlight that the choice of measurement seemingly retroactively determines whether a photon behaved like a wave or a particle, challenging naive notions of causality. As our journey through quantum mechanics draws to a close, a sense of quiet awe remains. The quantum world operates by rules that defy everyday intuition, waves that are also particles, states that exist in superposition, correlations that span cosmic distances. Yet these rules have been tested countless times and underpin technologies that define modern life. From lasers and MRI machines to semiconductors, atomic clocks and prospective quantum computers, the principles of quantum mechanics bring both profound understanding and practical power. The story of quantum mechanics is ongoing. Each experiment, each theory opens new questions. Through calm exploration, we glimpse a universe stranger and more intricate than classical thought could imagine. And we appreciate that our understanding is still growing. The quantum future promises to be as fascinating as its past.